This is StarTalk Sports Edition. I'm Neil deGrasse Tyson, your personal astrophysicist, and today it's a materials world. See what we did there? And we're going to talk about material science, what role it's played in the progress of sports, what role it will play in the future of sports. And let me first introduce my co-host, Gary O'Reilly. Gary.
Hey, Neil.
Gary's, gotta love Gary. We love your British accent, Gary.
Do you? Okay.
We do, because we're all jealous, because in America we have British accent envy here, just so you know. Okay.
We don't feel that envy at home.
And a former pro footballer in the UK, back where football means soccer.
Yes.
And so great to have you here in StarTalk Sports Edition. My other co-host, Chuck Nice. Chuck.
Hello, governor.
Worst ever.
You gotta love it, right? That's
You
how
gotta
bad
love
it is.
Okay, I don't think that's the accent we're all jealous of. Okay, that's I'll governor. No, we're trying to keep it, BBC English, not
Right.
Even Dick Van Dyke wouldn't go there.
No.
Dick Van Dyke, as in Bert in the
Mary
first
Poppins.
Mary
Right.
Poppins. Yes. Just for
Now, I have
everyone
my BBC
younger
side.
than 70 who wouldn't know that reference. Okay.
Oh dear. I'm being dinosaured.
Well, none of us have any expertise in material science, so doing the StarTalk thing we find someone who does. And join me in welcoming Jud Ready from Georgia Tech. Jud, welcome to StarTalk.
Thank you, Neil. Glad to be here. Appreciate it.
Excellent. You're an engineer. You got 3 engineer degrees right from scratch, bachelor's, master's, PhD. Let me just ask you, what % of engineering folk actually get PhDs? Because you're so employable at the master's level.
It's Jud. He's the only one.
He's the one.
It's just him.
There's a couple more out there for sure, but yeah, right out of the bachelor's, my students here at Georgia Tech are getting
They get
incredible
jobs.
offers, and they go on to great successful careers in industry. A lot of them come back to graduate school, either get a technical master's or MBA. My wife is an engineer. She's getting her MBA right now, in fact. And so,
Okay, so when you need money, you take out loans from them because you're still in academia.
yeah, I'm not making money off of anything that I do here for sure. I'm a state employee working for the government, so I get good vacation benefits, and that's about it. And really good internet connection.
There you go. But just to be clear, though most people who will consume this podcast will be hearing the audio rather than video, let me just say, on the wall behind you, you have an entire wall of plaques. And you told us offline that those are what?
Yeah, that's the Great Wall of Jud. Those are all the patents that we've received throughout my career. So 20 years now of work. Some are electronic materials, for instance, resistors in cell phones. Other are springs and mattresses. Some other are.
Well, don't tell me you can patent a spring. No.
Yeah.
No.
Microalloyed.
No.
Yeah. 3 of them. 3 of them up there.
3 springs.
3 of them. Fancy springs.
One is never enough, Judd, huh?
No. Lots of little springs.
So
That's like you walk into the patent office. I have this new invention.
and, right,
Springy.
and they say to you,
Microalloys.
and they say, "Hey, dude, that's a spring." Later.
It's
Come
a microalloy.
Come back when you got something.
got little dust of titanium and copper and all sorts of other stuff inside there with the iron and carbon to make it a.
So it's what the spring is made of.
It's the composite that you actually patent.
Yeah, the alloy, in
The
fact. Chuck.
alloy.
Yeah.
There you go. So let me get all your titles straight here. Deputy Director, Innovation Initiatives for
Yeah.
the Georgia Tech Institute for Materials.
That's right.
Adjunct Professor, School of Material Sciences and Engineering at Georgia Tech. Principal Research Engineer on the Research Faculty of the Georgia Tech Research. So you're in. You're all in.
He is.
All in on this.
Big
Been
stuff.
here at Tech for 18 years now, building up those different titles.
Nice.
And the problem is, all 3 of those jobs, all my bosses think that that's the only job. So I actually have three bosses and 3 jobs. So it can be a lot of fun sometimes, for sure.
Yeah, we'll
Really?
teach you about Einsteinian time dilation so you can fit all the jobs into the
Need it.
100
And I will teach you about cloning.
Let me just sing your praises explicitly and implicitly as a material science engineer. Practically anything that happens in my field, astrophysics, there's a headline. There's a black hole discovered, a planet is demoted, the universe is older or younger. Yet you guys are coming up with stuff all the time, completely transforming how we live. And hardly any of it is heralded. And I just want to just say that I've been watching you guys for decades and watching all of society shift to accommodate the materials that you're handing us and infusing into our products and into our lifestyle. And I just want to publicly say thank you for being this hidden heroes of the progress of civilization.
Well, you're very welcome.
Have you felt the steely gaze of Neil deGrasse Tyson over your shoulder?
There's just so much pressure now for us to come up with the next item. But we've been doing this for thousands of years. If you go back Stone Age, Iron Age, Bronze Age, right. All of these are named after a critical material. Information Age could be considered silicon, Nuclear Age, these other sorts of things. So as we go through time, the materials are extremely important to our evolution as civilization.
I hadn't thought about it, that the Stone Age, the Bronze Age, that's you guys. I hadn't. Yeah. So in the Stone Age, you guys were finding the right stones to use.
That would chip off and make flints, or that would smash a bone better than a piece of wood would smash a bone.
Or would make the cylindrical wheels of the Flintstones car. You see, you guys would have been...
But Doctor, what is new made of?
New?
Yeah, as in New Age.
New Age, certainly the composite materials are out there. A lot of advanced polymeric chemistry. And I'm not a polymer scientist as well, so I like to collaborate with some of my friends there.
You're trying to find things that are light and strong, basically, right?
That's the thing, particularly in sports, is the strength to weight ratio. Because we can make all sorts of things out of steel, but God, a football player wearing steel armor playing football, that's just not going to make for a very exciting game after much longer.
That's called a knight.
The knights in armor that can't get up once they fall. So your specific specialty from my notes tells me that you think of carbon nanotubes.
We do.
And just remind people what those are, or tell them for the first time.
A carbon nanotube is, if you're from the South like I am, is chicken wire, a hexagonal lattice of carbon atoms that are then rolled into a cylindrical tube. It's roughly 10 or so atoms across if it's a single wall nanotube across the diameter. A lot of the carbon nanotubes we grow here in our lab are multi-wall, so it's like an onion or a Russian Kachina doll where they're nested amongst each other.
So this is there's no other atoms involved, just carbon making this six-sided hexagon that is tiling the wall of a cylinder. Is that what you're describing to us?
Yeah, that's the goal, is to have nothing but carbon bonds forming these hexagons. There's often always some defects. So instead of perfect hexagons, you might get a few pentagons in there with some dangling bonds that then attach to oxygens and hydrogens in the atmosphere.
Would that create a weakness in your structure?
Structurally, yeah. I primarily use the carbon nanotubes for their electrical applications. We focus on energy capture, storage, and delivery for aerospace applications with an emphasis on the space. So energy capture, like solar cells, which we just had a mission come back from the International Space Station, just splashed down last week. Wow. Going back again in August.
There's something just happened in that sentence that I just want to put it out there, okay? Our space shuttle, which we no longer have, no longer fly, landed on a runway. So when our astronauts came back from the space station, they would land. But now our access to space is either by Russian capsule or SpaceX capsule. Both of them, Russians land. Well, they don't splash down, but they slam down.
Yeah, it's rough.
On the ground. So rough. Mm-hmm. Them Russians, boy, let me tell you.
They're tough. They are.
They don't land on water. They land on solid ground in a capsule. And SpaceX has returned the tradition of landing back in the water, splashdown. So I just hadn't heard splashdown since the 1960s. So it's great to hear that.
Yeah, and so the energy capture our solar cells, we use the carbon nanotubes to form a light trapping forest, if you will, that we then coat the carbon nanotubes with a photoabsorber. So the photon of light can pinball around inside that forest and eventually get absorbed. So it essentially increases the dwell time of the photon in the photoactive layer to increase the charge conversion.
So these tubes are hollow.
The tubes are hollow. We're using them just as a wire, really, as a scaffold to put the material on that absorbs the light, and then as a electrically conducting member to extract the carriers out of that.
So are nanotubes in my life right now in any way that I can think about?
Yeah, we've used, you probably don't recognize it, but they're very good electrical, thermal, and mechanical properties. So they've been incorporated into trays in silicon fabrication facilities to carry samples around to reduce the static buildup there.
So they're basically as trivets.
They put them in tennis rackets. Babolat had a tennis racket in the early 2000s that included carbon nanotubes.
Just to be clear, we're not talking about carbon fiber here, which we've all seen. There's carbon fiber bicycles and carbon fiber cars, fuselage, plane and car bodies. So that's not what we're talking about, right?
Nope. These are individual carbon nanotubes that have then been composed or combined with a matrix material to strengthen a composite structure. I wonder about the actual performance there. I think there's a lot of advertising benefits, certainly for including the carbon nanotubes in your tennis racket or baseball bat. But the applications we're looking at are very specialized to take advantage of the low work function of a carbon nanotube, for instance, to emit electrons to serve as a cold cathode for satellite propulsion and a Hall effect thruster, for instance.
Damn, I would not have ever imagined how many different ways you could use nanotubes. Yeah. And it's probably only just now plumbing the surface of what of where it could go. So how now sports is always trying to, faster, higher, stronger. Have they reached out to carbon nanotube people for anything?
Yeah, certainly have looked at it. Again, like I was saying with the tennis racket and the baseball bats as well. There's questionable benefits from a mechanical perspective. I think there's really strong benefits from a thermal and electrical benefits to incorporate it, as opposed to, say, carbon fiber, which is very, very common, or graphite. Which is just very pure carbon fiber typically.
Graphite that's what's in my pencil.
Yeah, but you can make it into a fiber structure. So you take the carbon fiber and you purify it even more so that it's, instead of 95% carbon, it's more like 98 to 99%.
Well, that would make an awesome pencil. I'm guessing.
And jackets. I can draw something with my jacket sleeve.
So what branches of sports are most touched by this, do you think? Or will be in the future?
Let me guess. Race car driving.
Oh.
Always.
Yeah, they've got deep pockets for sure on the automotive worlds. The more professional sports that can stand to invest in things and to have localized applications of carbon nanotubes, say in a helmet or padding, and those sorts of things. I really have not looked at getting my own materials into sports equipment. I've tried to use some of the established ones out there that are like commercially viable, so that we can quickly get these innovations into the hands of the public. It's really interesting how advanced materials like a carbon nanotube or a titanium or carbon fiber starts out in the military typically, and this goes back to Bronze Age and Stone Age as well, and then it advances into a commercial application. That's very commonly sports. Titanium, carbon fiber, that's often found in bicycles and other sorts of equipment like golf.
Judd, just to take a step back, the applications you've just expressed, I hear terms like matrix, which gets my ears pricked up. Then I get into C triple bonds, and then I hear ABS, which sounds like something that comes on my car. But can you break that down? Because I'm sat there bewildered by a new language.
Sure. So when you create a composite structure, you combine two different materials that have desirable traits that when you combine them together, you take those desirable traits to another level. It's not simply additive; it can often be multiplicative. And so you will have a fiber reinforcement, like a fabric, as well as a polymer, like an epoxy. And so that epoxy can form what we call the matrix. And what that does, that shares the load between your plies of fiber or your individual threads and whatnot. And the different polymers will have principally a polymeric component, has a carbon-carbon chain sequenced along. And some of those carbons can be bonded with a single bond together, for instance, like a polyethylene, or if you have a double bond between the two carbons, for instance, like an isoprene, polyisoprene, that can make up, can stiffen the polymer. And so it can have properties like a golf ball that will be much more rigid than, say, a latex that has a more rubbery.
This is like you're in a kitchen and you say, oh, I need this strength and this flexibility and this way, and you're just pulling out chemical bonds of your ingredients, mixing it together to make exactly what you want and expect to have.
And that's what the ABS is. ABS is a very common polymer in helmets, in ski boots, and a variety of other things. And the A and the B and the S all stand for an individual polymer that have been grafted together to form what's called a copolymer. So A is acrylonitrile, which has a C triple bonded with N, which is a very stiff bond. And so the acrylonitrile provides a lot of stiffness.
When you say an N, you mean a nitrogen atom?
Yep. Sorry.
Okay.
Exactly.
So CN, when I think of CN, I think of
Chuck Nice.
Cyanide.
Chuck Nice.
Hey,
That's good, Chuck. Very good, Chuck.
you set him up, he'll knock him down.
Damn, Chuck, that was quick. When I think of CN, I think of what's the
Cyanide.
poisonous gas? Yeah, cyanide. I think of.
Yeah. It's and
Just yes. Okay.
it is. Yeah.
Exactly.
But it's bound up in the structure, so it's not releasing.
So it's safe. Okay.
Yeah.
Right.
As long as you don't eat your ski boots.
Still don't sniff it.
Yeah.
Whatever you do.
Don't smoke the don't smoke the
Don't
boots.
smoke it.
Smoke the ski boots.
So, well, how about this, Jud? So, is there any advancements being looked at for these polymers or even these the nanotubes to change with physical surroundings, like they become stronger when they get colder, or they become more fluid when they get hot?
I love those when they do that. I love those.
Sure. Kevlar is actually one of those that does get stronger when it's colder that people are familiar with. There's other ways that you can have what are known as shear thickening or shear thinning behavior, so that when a stress hits it, it either stiffens up, which can be useful for a shock absorber or something like that, or it can thin out and provide a cushioning impact. For instance, say in panels by a race car around a racetrack or something along those lines.
They're perfect for ice hockey.
As well.
Wait, why? What do you need for ice hockey?
Ice, cold, padding, Kevlar. If it gets thicker as it's colder, so you stick it out on the ice, then it's going to be good. Surely.
Wait, when I think of Kevlar, I think of something that stops bullets. So is this the future of hockey when people shoot
Ever
each
seen
other?
a
I was going to say, he just made hockey the most interesting sport to me ever now, because instead of just sticks, you play with guns too. It's awesome.
Well, I mean, you get hit by a
new
puck.
thing to the fight.
Exactly.
I mean, you get hit by a puck that's traveling at over 100 miles an hour. That would be classified as a lethal weapon.
My wife, when she took her very first trip away, left me at home with our very first baby.
Wait, she's also an engineer, correct?
She is an engineer, civil engineer right here at Georgia Tech. She got hit by a hockey puck at the hockey game. And so she took that as like a sign from the gods that maybe she shouldn't leave the baby with dad for.
Well, she should have took it as a sign.
I didn't hit you with a hockey puck, baby.
I was going to say, she should have took it as a sign to give up watching hockey.
But she after it bounced off her arm, some dude took it from her. She's like, "Hey, that's my puck. That hit me." And so she got it from him because she's a strong-willed woman. And yeah, very much so.
You ought to be able to
That's
keep
why I
the
married
puck that you get hit with. I think.
And yeah, it's our daughter's teething ring. Our daughter's now in college, but back then, it was their teething ring. We washed it. We cleaned it.
Oh, well, that's okay then.
Yeah, that's amazing.
Wait. I'm sorry. That's a scary. No, that's like superhero baby. If a hockey puck is your teething ring.
I'm sure we still got it. I'm sure it's
That's
somewhere.
amazing. It's just like you cut your teeth on the thing that almost killed your mother.
All right, we spent all this time talking about the materials, and let's, in our next segment, bring up all the ways that they will specifically be implemented in the present and future of sports when we come back on StarTalk Sports Edition. We're back, StarTalk Sports Edition. Got Gary O'Reilly.
Hey.
Got Chuck Nice.
That's right.
My intrepid co-hosts, and today we're talking about material science because it's a materials world. And we've got a material scientist in our midst, Professor Jud Ready. Jud from Georgia Tech. Welcome back to StarTalk.
Good to be back.
Let's
look forward to some more discussions.
Yeah, more discussions. And if you've been at Georgia Tech for a while, at least, or a Georgian, at least since the 1996 Olympics.
Yeah.
And so they've got a track down there. What do they call it? Mondo track?
Mondo.
Vulcanized rubber. Tell us about what that did to the performance of track athletes.
Yeah, the Mondo track is really a key innovation. I was actually a graduate student at Georgia Tech when the Olympics came, so that was a fun time to be here. And as part of my class that I teach now here at Georgia Tech, the Material Science and Engineering of Sports, we take field trips to all of our different facilities in the locker rooms and equipment rooms. And one of the popular ones is our track. So Georgia Tech was the Olympic Village, and so all the athletes were here, and they needed tracks to train on. And so we got an awesome track out of the deal. The difference between, say, an asphalt or a concrete track that many existing tracks is using local materials. You got the concrete aggregate and everything came from somewhere in that general vicinity, and it's laid down sequentially in a series of rows from lane 1, 2, 3, 4, so on and so forth. And so the uniformity around those different lanes differs. So the durometer, the amount of spring that's in the track, changes whether in your lane 1 or lane 2 or you're at the start or the end of lane.
Durometer, that's a word.
Ooh.
That is a word. That is a word.
And what does that mean, durometer?
It's the return of energy. Is a good way of thinking about it. The springiness of the track.
So the durometrics of the track. Oh, I love that. I love
and,
it. Okay. So in other words, when you run, there's energy that's lost on the recoil or energy that's returned to your bounce, I guess. And if you can get 100% of your energy to come back, that would be pretty good. Maybe too much, perhaps.
Yep. You'll see this a lot of times. People running will run, even though there's a perfectly good sidewalk, will run in the street with the cars because it's softer on the joints, for instance.
Yeah.
So the difference with Mondo than the asphalt, which are laid sequentially over a period of several days, so the humidity changes. Wait,
sorry, I have to interrupt. You just distinguished the softness of asphalt in a street from the hardness of concrete on a sidewalk. Did you just do that?
I did. I did.
Okay. So to most people, they're both hard. So tell me where you're coming saying that asphalt is soft and squishy relative to the cement-laid concrete of a sidewalk.
Yeah, it's just different chemical bonds. The asphalt is typically a petrochemical based solution, so there's a lot of hydrocarbon acid, oil. Exactly. Whereas the concrete,
crude oil. Okay.
Yeah, concrete's typically more silicate based, and so it's a much stiffer bond. And so as you step on it, no matter what type of material you apply a load to, the bonds between the atoms compress or stretch if you're pulling on it. And just the degree to which those stretches can be macroscopically manifest themselves to a feel that you can feel when you're running on it.
Okay, so this would be the difference between if I took a hammer and hit an asphalt street. It's a very different sensation if you take a hammer and hit a sidewalk.
And sound.
And a different sound, right?
Correct.
Right, exactly.
And also the asphalt typically has very large aggregate. Like you can look at the asphalt and typically see the grain
blobs.
structure, if you will.
Yeah.
Whereas concrete will be much smaller, and the smaller the grains you get, typically the stiffer and stronger material.
Okay, so your Mondo track is even better than asphalt. Here's what you're saying. Okay.
It is.
In that same direction. Okay, so keep going. I interrupted you. So on.
No. The Mondo track has excellent quality control. So it's made in a factory, much like carpet, as opposed to created on site. And so the width of it's usually two lanes wide. It's uniform all the way along the length of that piece of carpet, if you will, that's laid out, as well as the width. So no matter what part of the track you're on, always have the same durometer, the same mechanical performance, and the same response to the environment, for instance, shedding of water and those sorts of things. And
okay, so it's the proverbial level playing field. Yeah, there you go. Okay,
it does.
Keep going.
It does. And so the Mondo also has a really good lifetime. Despite being a polymer, polymers typically are not the best choice outside because the ultraviolet radiation will attack that carbon-carbon bond, as well as some of the other carbon bonds. And the Mondo has.
Well, I just have to jump in there because in my field we think only ever about what light does to things. So correct me if I'm wrong, Jud. So there's the strength of any chemical bond between two atoms. You can measure how strong that is. So now you have light coming in this case ultraviolet, whose energy is greater than the strength of that bond, and it'll just break the bond. That's what's going on there. So if you had different kind of light, like visible light or infrared, those photons don't have enough energy to break the bond, and so the bond is safe in the presence of that light. Is that fair to say?
Yes, and different polymers respond differently. So sometimes the ultraviolet will break the bond. Other times it will
makes it harder.
It'll create additional cross links. Exactly right. And so
that's what dentists use to affix fillings and things like that. They use ultraviolet light to seal the bond.
Yep. And so that can take what was once a nice, flexible, pliable, rubbery-like polymer and make it very, very stiff.
Okay, so this is just the genius of folks in your profession making stuff happen that you want to happen.
Yeah, and trying to avoid the ones that we don't want to happen.
Command over chemistry. It's brilliant. Okay, so keep going. So all right. So now it lasts a long time and it's uniform. So what? Why would I run faster on such a track?
Oh, it's got good energy return. That again, the springiness, but it's really the competitive fairness that plays in. The thickness of the track is maybe a couple inches thick or so, but just the uniformity makes for a vastly superior product. That it's not just the track here at Georgia Tech is uniform, but the same track that they put, say, up at Emory University for practicing on had the same amount consistency of the properties, which has the same ones as downtown at the Olympic Stadium. So
if I ran a world record at Georgia Tech in lane
will
one,
they count
I'd probably run the world record in lane 6, and I'd probably run the same world record at Emory, but that may not be the case on other tracks.
Correct. And I've seen several tracks. My daughter was in the marching band that we'd go around and just see some terrible looking tracks that, the asphalt's just crumbling up and just doesn't provide the quality of feel. And now it's an expensive track, so high schools can't be expected to have a Mondo and that sort of thing. But I got
to know if it's all about returning the energy to the runner. Is there a limit beyond which it will not be allowed as a record? Is there some rules about how good you can be at your job helping athletes?
There are a lot of rules that are placed onto a lot of different materials that are used in sports, from golf clubs, golf balls, baseballs. All of these things will have metrics on them. Javelins, for instance, have javelin got to be really good that people would basically start throwing them into the stands, which is really rough for spectator morale on that.
Yeah, that was a guy called Jan Zelezny. a European guy, I think it was Hungarian. He was throwing it about 90-something meters. So if you were high jumping at the far end from where he was throwing, you were in danger.
Oh, 90 meters is the full length of the track. Right.
And then some.
So they had to add like aerodynamic drag to it.
Yeah, they made it worse.
Why don't you just have them throw them outside the damn stadium?
Yeah, it's like a restrictor plate in NASCAR races and stuff like that. So it's anathema to me as a material scientist. It breaks my heart when they start dumbing down my materials. And
I gotta say though, it's a hell of a lot worse than a hockey puck.
Because you can't chew a javelin as a child, can you?
No, it's a heck of a toothpick.
Well, I keep wanting to move on, but let me just get one thing out there. So, in principle, you could design a track that returned 100% of your sort of gravitational energy as you run from step to step. If you did, if you can, why don't you?
Well, certainly cost would be an issue, but that's what you're describing is the trampoline effect. It's used in tennis rackets, baseball, softball bats, golf clubs, and so you just have a thin material that is able to reflect or respond to the energy that you impart upon it. Now,
so why aren't tracks trampolines?
Well, you begin to get into you need some resistance to push against. Like if you've ever tried to run across an actual trampoline.
Yeah, it's hard. I tried that
it's
once.
Not so much fun sometimes. So it's engineering trade-offs. You have to balance it out to a certain.
But once you get a good bouncy thing going forward, it could. That's a different kind of race.
It looks like a race on the moon.
And that's just it. You going up and not forward.
Oh, yeah, that's right. Because you need the friction to go forward, whereas the trampoline is really good at making you go up.
Yeah, for instance, you could have that better, more springy substance near the high jump pit, for instance, where where you're not as worried about your forward motion as your upward motion.
Or you can have your starting blocks could be a pre-cocked trampoline facing forward. Ooh, that would be good. So your first step. So you don't have this time where you have to get up your speed. You hit your top speed instantly. That'd be cool.
Fires right off.
We should make that happen.
And Chuck, you want what kind of big cat behind the blocks? 100 meters.
No, I mean,
we talked about that. Yeah.
I would just like to see people shot out of the blocks if I could. That'd be better.
No. And then you open a tiger cage, and then they're running after you. Will break records all the time. But let's get back to the other things. For example, recently. When exactly was it, Gary, when the 2-hour marathon record was broken?
This goes back to the doctor's point about banning materials and not seeing the sort of constrictions. Nike have a shoe out called the Vaporfly, and I think they've even called it the Alpha Fly. And the dream has always been break 2 hours for the marathon.
Right.
And 2019, Koji, the Kenyan runner, who's 34 years of age, broke the 2-hour barrier by about 20 or 40 seconds. And he did it wearing Nike shoes, and there's uproar. But the thing is, the thickness of the sole, but they've got a little special ingredient, Doctor, don't they? What have they put in those Nike shoes that makes them so special?
Yeah, that's they've got
Kenyan DNA.
They've got that for sure. They've got carbon fiber plates in the base that provide an energy return. And I'm not a runner. I only run if I'm being chased. So that doesn't happen too much anymore. But the return of energy through these series of plates are as much like a spring. And just the concept of a 2-hour marathon, I mean, that's 13 miles an hour. That you're averaging running through there, which is a very fast, just regular run.
Yeah.
So this record was broken, but I wouldn't say smashed. So 1 hour, 59 minutes, 40 seconds.
But the thing is, Neil.
So why are people complaining? Just everybody wear the Nike shoes. So what?
Because
Nike does it first. Everyone calls it Kleenex. They did the pop-up tissue first. So Band-Aid, if you do it first and best,
right? Just
I don't have a problem
the technology
with
that.
These are the rules. These are the rules. You see.
Damn.
The technology has to be available to basically everybody. If you want to compete in these shoes, they have to have been available to the public for something like 4 months prior
That's correct,
to the event.
Which I don't, it's a competitive advantage. I mean, that's the whole thing about competing is you're trying to be better than somebody else.
No, stop.
Okay,
Stop.
Neil's not happy.
The
here we go.
shoes don't have rockets in them.
Not
The
yet.
shoes
They're magic
don't-
shoes.
It is your energy. It is the management of your running energy in the soles of your feet. So it is still me running that distance in that time. Now, it'd be something different if I had rockets and stuff and
You don't
jetpacks.
need Neil. You don't need rockets when you're elite, and I'm guessing because I've never been there at that level. Because don't forget, Kipchoge breaks the 2 hours. He already holds the official world record for the marathon, right? Nike claimed something like 3 to 4% improvement in your race times. Now, for an elite athlete, that's a gold medal.
It helps.
That's the-
It helps us non-elite athletes too.
Yeah.
I have.
I get
an
it.
issue
For
with-
me, that would just be finisher.
All right, let's, we
T-shirt.
I
we
just
got
have an
more
issue
things
with
here.
people doing that because let's just run barefoot. You know, if you
Yeah,
got
I was
issues
about
with
to-
shoes.
I was about to say, the guys from Kenya, I mean, somebody is going to break the world in 2 hours without shoes, period.
Without shoes.
Oh, no, they did.
They're not even going to be wearing shoes because that's their culture. But
No, they do. I mean, back in '68, Gabriel
the winner.
Selassie ran barefoot.
Yeah. In fact, he started out with shoes, if I remember correctly, and he just didn't like them because they were brand new shoes. And he just took them off and finished the race. You know.
Wow.
There you go.
So we got to keep moving through these topics.
Yeah.
So tell me about what's the status of golf balls now?
Golf balls is one of the most fun labs that I have during my class. I've got some examples here. So they started out way back in the 1400s as knots of wood and rocks, which golf is kind of a miserable sport anyway. It's amazing that it took off when you're hitting rocks of wood. Imagine putting that thing. And so then they got slightly better where they boiled goose feathers and stuck them inside a bladder and made these things called featheries. Those had much truer flight, but you introduced the situation where you would literally explode the ball if you hit it too hard. Plus, if you hit them in the water, despite being goose feathers that were boiled, that made your ball soggy, so you couldn't use it anymore. They then moved on to what's known as gutta percha, and those are the so-called gutties golf balls, which was a polymer. It's a naturally occurring sap from the tree, the gutta percha tree. And that produced a very uniform ball that could be made in large quantities. Then they started to incorporate additional things. For instance, this one's all rolled up now, but it has basically a rubber band that's wrapped around a solid core inside it. And that provides golf is a game of feel, as they describe it, so that there's benefits to rolling and backspin and other types of aspects of flight. Now they've got a variety of polymers.
Wait, just a sec. So baseballs were for a while, if not still, were also a rubber band wrapped around a core.
Got one right here.
Oh, okay. So he's holding up a. Did your dog chew on that baseball?
No, this is a Georgia Tech baseball that for my class we took it apart because we were highlighting the differences in materials. As sports materials have gone along, they almost always, or they do always, start out as natural materials, wools and wooden materials and leathers.
And baseball gets the award for natural materials using wood bats, leather gloves, pine tar, spit,
cotton fabric in here.
Yeah, they're untouched by your magic.
Yeah.
In so many ways.
Which is really disappointing because we can make an awesome baseball, let me tell you.
I was going to say, no wonder baseball's so boring.
Yeah.
So what is the latest golf ball costing us? The latest, greatest golf ball?
Oh, man. It's this 5-piece ball here. So it's got 5 layers of different material in there, providing a very hard center for your carry. The outer shell will have some UV stabilizers. So again, so that the ultraviolet doesn't harm it, but also so it has lower friction as it flies through the air.
Just so you know, this cross section of the golf ball, the latest golf ball that you're now showing me, is it looks like a cross section of of a planet.
It is. And they talk about the mantle and the crust.
They do. Yeah,
and
there
the
you
core.
go.
Yeah, that's exactly how we describe it. And just like the Earth, each one of those layers has a different consistency and mechanical properties to it to provide either the dense mass to have some carry or a little bit of resiliency to it so that you can induce spin onto the ball.
So once again, you're combining multiple properties to get one generalized effect that
Correct.
people seek.
Correct.
So is that the future of golf, that golf ball?
The golf industry is regulated. They don't want the golf balls to fly too far because golf courses are very expensive to build. So, suddenly your
once
par
again,
5 is now a par 3, and you got to buy up the neighboring lots and other sorts of things. So, no, it's serious. And again, as a material scientist, I've got issues.
Imagine you've bought your beautiful golf course in a beautiful part of the world, and someone comes along and they now start to hit it 500 yards. And your golf course is built for maybe a 375, 400
That's because
yard
assholes
power
like
hitter.
Jud Ready are making my game better.
So you can't go buying up land around your golf course because it's just too expensive. So all of a sudden,
Especially because you can hit it 500 yards into the woods. And so now it goes like over the guy's house into the next yard beyond that.
Okay, so how about the poles they use in pole vaulting? When my father ran track, I think they were bamboo or something, right? I mean, we've come a long way.
I was actually a pole vaulter.
Wait, your father didn't use bamboo, did he?
No, when he ran track, his fellow track athletes were using bamboo who were
Oh my God.
the original poles were bamboo, Chuck.
Yeah, bamboo was up until just a little bit after World War II.
Holy crap.
Yeah, that's when he was there, yeah. In fact, the baton was made of bamboo in the relay races. So,
that I can see. I mean, I'm not trying to,
I'm just telling you how natural materials were still infusing what we were doing. So what are they made of now?
Yeah, now they're composites. So they went. It's really a great story. If you look at the world records, you can see clearly the bamboo era, then it stops, and then aluminum, and then it plateaus out, and then now we're in the composite area. Because you can take those composites and just like we were talking about the energy return, you can preferentially put reinforcements where that pole is bending, as opposed to an aluminum, which would be uniform throughout the properties throughout the length of it. And so you can preferentially put springiness where you want it to have greater and greater heights.
Could you ever make one so springy that, like the javelin, you could just pole vault out of the stadium?
Yeah, well, pole vault has some great rules. The pole vault basically has no rules whatsoever. The only rule is that you have to carry the pole. Like you have to carry it in yourself. So you can make it out of any sort of material you want. Now there are some good wisdom, and you want to have this certain diameter pole for your weight and your style of jumping where you want the pole to bend so that it doesn't fracture, which are some of the most incredible videos that I show.
Highlight videos, yes.
Oh my goodness. Yeah.
It's the only reason to watch pole.
Chuck, you are so sadistic, Chuck.
It really is.
Well, that's Chuck. Chuck's got to have a reason to tune in.
Okay, wait.
I've never watched
So
pole vaulting.
okay, Doctor. Before we jump out to a break,
We got to jump out to a break. Go quick.
Can you build a kick point like a hockey stick into a pole vault and get that extra?
Sure, they already do that.
leverage?
Yeah, that's standard. They very much reinforce specific areas of the pole to do it.
So the pole is not a uniform
No, not at all.
material from bottom to top. Ooh.
Which is why if you carry it the wrong way, you get a whole different outcome.
Definitely make sure to put the right end into the pit. Reverse it and put the wrong end. That leads to
And just so you know,
excitement.
a former guest, a brief guest on StarTalk, Buzz Aldrin, the Apollo 11 crew to the moon, he was a track and field athlete and did the pole vault when he was in college. So just thought I'd say that before we go to break. When we come back, more of StarTalk Sports Edition. It's a materials world. We're back, StarTalk Sports Edition, with Jud Ready, our special guest today, a material science engineer. And of course, I got Gary and Chuck, my co-host. Gary and Chuck. All right.
Hey.
So this is what we call the shoot the shit segment, where we just sort of unpack so much of what we've just discussed. So first of all, our crack team of researchers reminded us of who finished the marathon in bare feet. It was 1960, an Ethiopian, Abibi Bikila. So
Yes.
it was not 68
Not,
on that
yeah,
one.
sorry,
I think.
apologies.
Yeah, yeah. So, but that's, it was close. He was black and from Africa. So
Yeah, exactly. So it wouldn't make a difference what year it is.
Stop that.
Oh, come
it
on,
wouldn't make a
guys.
difference what year it is. You know it's going to be some black dude from Africa.
Ah,
all
I
right.
apologize. I didn't get the right athlete. That's my bad.
Haven't you seen Chariots of Fire? I mean, come on.
No, yeah, in the
Those dudes
movies.
were wearing shoes.
and it was in the movies. That
And
happens
on
in the
cinder
movies.
tracks, not any Mondo or even asphalt.
My father ran cinder track, yeah, and he would tell us about if you fall, the cinder would
Trouble.
go under
Yeah.
your skin, and
That's
you get
horrible.
It was very, very bad. A point we didn't get to in the second segment. Let's see if we can dispatch with this quickly. Tell us about Sharkskin swimming suits. What's going on there?
Yeah.
Yeah, so Sharkskin, that made a big deal in the Olympics. It was a suit that it was polyurethane was principally the polymer that was involved, and that has the benefit of floating in water, and so it provided assistance to the swimmer to keep them from drowning, basically, so that your energy could be focused on going forward.
Wait,
rather
I
than-
never knew that because swimmers have very low body fat, and body fat floats and muscle sinks.
Yeah,
So-
I mean, it wouldn't hold. I mean, you couldn't float like you were in the Dead
No, but a
Sea or
little
anything
bit.
like that. But
It's a little bit matters.
correct, it does. At these levels, a fraction of it does. So that was one benefit, that it was just inherently buoyant.
Wait,
Also,
so why don't they just wear one of those life preservers?
you got two little bit of drag on that
How
one.
about swim? Just go with swimmies.
Swimming, right? Wow. Okay. So I get that. So they're a little more buoyant.
Yep.
So their
But they were
energy-
also hollow. The fibers themselves were hollow, so air could be entrained as well. to
That's
provide
how they.
additional-
That's how they get the buoyancy because
And
the
then-
fibers are hollow.
And then furthermore, the topography, the surface characteristics of the swimsuit had texture on it that would disrupt the boundary layer where the water is touching the surface to transition that between laminar and turbulent flow, so that it released, and so that there was.
So
less
this is
friction.
like the surface of a golf ball.
Correct.
Same thing.
Correct.
Right.
It separates the flow of the fluid around it, whether it's air for a golf ball or water for a swimmer, to allow less friction.
So was it outlawed when it first happened? I catch me up on the news on that.
It lasted for an Olympics, and a ton of records were set all during that period of time, with asterisk marks and everything next to them now, I'm sure. And then they just said, no, that we can't have this. The other thing is they were full body suits that they provided compression, so it reduced the cross section of the swimmer, like it squeezed them in, so there was less friction through the water. But the compression also increases your muscular ability. So there was a whole bunch of really good benefits. And
Sounds like everything's good. What's the problem?
I know. What's the problem? Again, they're putting you out of
nothing
work.
if I'm a material scientist.
Exactly. Exactly.
Yeah.
But the
All right.
problem was people not, they want to make it, I guess, fair for everybody to have accessibility to these same things, much like the shoes have to be available. And so that
So
was one of the
everybody
things.
gets a suit.
So
It'd
everybody
be
gets
like
a
an
suit.
Oprah show.
I'm
You
with you,
get a
Chuck.
suit, and you
Chuck,
get a
okay.
suit, and you get a suit, and you get a suit.
So okay, so you guys must have a museum of the cost of being too good at your job, of the things that got stopped because you represented too much of an advantage over everybody else.
Just the man
That's
keeping
a-
us down. I'm really tired
That's
of
a sad museum. Okay.
All right, Doctor. I mean, maybe it's just me. I've long held this idea of electronically powered garments, whether they would change color, whether you could change sort of advertising on uniforms or whatever it is. Apart from a battery pack stuck to the side, which isn't really efficient, where are we now with these sort of things? Or am I just going to continue this dream?
No, we can begin to capture energy from all sorts of sources. Obviously, solar power is available,
Right.
But because you're in a sporting event, there's a lot of mechanical energy available. We already talked about kind of the passive return of energy through the shoes, but you can use what's known as a piezoelectric material that converts mechanical energy to electrical energy, like a quartz, for instance. You can do that. You can also have electrical that converts to mechanical. So you can capture that energy and then store it in a usable manner, such as in a capacitor or a battery, to deliver that, to provide communication capabilities. For instance, a Wi-Fi or a Bluetooth type communicator to transmit athlete health performance. Simple stuff like respiratory rates and heart rates, or more complex things like pH of your sweat or the amount of adrenaline or other sort of stress-inducing or stress-signifying chemicals that the body secretes.
Now, I always thought that at a fitness center where they have sort of the treadmill and you're watching TV, that you should be powering that television.
Oh, yeah.
Yeah.
And so,
Correct.
and if you stop working, the television shuts off. So if it's your best part, that means you got to keep going. And what really should happen is all fitness centers of the world should feed the energy back into the grid.
Correct.
Look at how much energy we're burning and not doing anything with it.
That and capture the kindergartens too, because there's a lot,
That's where all the energy is.
there's a lot of bouncing around in those kindergartens for sure.
Yeah, you'll have child labor laws for that, for sure.
Yeah.
But no, I mean, are we going to get to this point where we get super smart clothing?
Yeah. I think that's where we're at right now. Is the history of sports has always been about strength to weight ratio, and so that's why we've got composites, and we're using the light metals like aluminum,
And that
titanium,
phrase,
magnesium.
strength to weight ratio, is you want as much strength as you can with the least weight.
Correct.
Because putting something into motion, you can make it go faster if it weighs less.
Correct.
And you can
Exactly
accelerate it more nimbly if it weighs less. So I just want to clarify, strength to weight ratio encapsulates all of that. Right?
Yep. It normalizes it out and makes it, that's the reason why we have titanium. Titanium is not inherently better than steel from a strength perspective, but it's way
Lighter.
less. So it performs better when you normalize that.
All right, so let me ask you this, talking about strength to weight.
Wait, one other thing. Wait, before you go, Chuck, I need you to verify what I've been telling people, but you're a materials guy, and I just want to put it out there, okay? Everyone thinks titanium is some magic new substance, but it is one of the most common ingredients in Earth's crust.
Yep.
And it's just that it took us a long time to figure out how to extract it in an affordable way to be used. It took us a while to figure out how to make it economical.
Yep.
So is that a fair statement?
That's a very fair statement. Just because it's prevalent in the Earth's crust, much like rare earth materials sound like they should be not abundant. They're everywhere, but they're not in mineable quantities. I mean, it needs to be concentrated in a place where you can dig out just many, many millions of tons of this material.
Right. By the way, thank you, China, because they pretty much own the rare earth
That's true.
business now. So
That's pretty much true.
Yeah. Once again, America falling behind.
All right.
America.
Yeah, but
so-
get back to what Gary said. Everything was strength to weight, but where we're going in the future is multifunctionality. That it's more than just mechanical benefits. We're wanting to look at the thermal benefits, particularly as it applies to uniforms and clothing, or say tires on a race car or a bicycle. You want to capture the electrical opportunities to have sensors built into your clothing. I mean, we've got it now with a Fitbit, but could we have it inherently within the structure to capture body temperature or respiratory rate or things like this? And then one of the biggest ones, and people giggle about it, odor control. I've got a design component of my class here at Georgia Tech, and the athletes.
That's called the BO class.
It is. It is over and over again. The
I just ran a marathon and I smell like lavender.
You rode the taxi cab, Chuck. That's the thing hanging from the mirror.
Yeah.
So let me ask you this: strength to weight, both you and Neil. So in baseball, you hear some players talk about they want to use a heavier bat. Is that preference, or is there a mechanical advantage for a player of a certain size to swing a heavier bat, thereby letting me ask you, can something be too light even though it is strong enough to do the job?
In fact, let me reshape that question for Jen. If so, I have a certain strength, right? And so, should I swing the heaviest bat possible, where I can still come around to make contact with the ball?
That's the key.
Or should I swing a lighter bat that I might be able to swing twice as fast, for example?
Yeah, most players prefer a much heavier bat, but you can't get it around in time. So it's very much a personal preference to get it down to a controllable weight. But you want it as heavy as possible.
So there are two competing factors there, is the point.
Yeah, there's clearly a crossover point, baseball players are so freaking superstitious anyway that you can't change their bat at all anyway. But to be able to scientifically assess how you hit that bat, that's some of the stuff that people are doing now to match the club with the player like they do in golf.
All right. So how about the fact that in any expenditure of energy of the human body, the body temperature warms, and as such, the body temperature now wants to cool itself. Can you have clothing that whisks away the extra heat and then converts that? Is heat energy so low quality that you can't do anything with it at that point, and you just got to dissipate it?
It is a challenge. Certainly having delta T, the difference in temperature, have a hot and a cold, you can do something with that. The inherent prevalence of the heat itself, generally you just want to get it away from the athlete. And that's some of the technology we've been developing at Georgia Tech with some research partners that promote wicking through the fabric. We've got a student of mine that he was a wide receiver and realized that fumbling a football is a bad thing as a wide receiver.
Mm-hmm.
And so he created these they're called lizard sleeves that has a sticky side, if you will, on one side and a slippery side on the other side. So the slippery part you put on the exterior, like the defender side of your forearm.
For tackling.
Yep. And so you can shed the defenders with that, whereas the sticky side is on the ball carrying side, so that you can hold the ball better. Now it's not a coating or anything. It's a knit. It's what's called a warp knit. So there's several different fibers in there, and the way the knit comes together, the sticky fiber, which is a spandex type fiber, is on the outside of the surface. So that coating can't wear off. It's just inherently built into the structure. And
once again,
inside
being
of the fabric.
clever. Were you so clever that they now outlawed it? What's the future of that?
Not yet. And so
Not yet.
Yeah, exactly. It seems like they rule everything out. And so we're going to make a go of it for the next 5 years till they create a rule against it, probably.
Damn.
But the knit was important because you can't have the sticky on the inside because you wouldn't be able to get it on your sleeve.
Right.
So it needs to be slippery on the skin surface. Now, wide receiver gloves have a similar tacky-like construction. You can't
Which allows them to just stick their hand up high above the head and the ball just sticks to the hand.
Yeah, you can't use stickum anymore. That's been outlawed, but the wide receiver gloves are still okay. Those have silicone pads on the fingers and the palm. This is not an add-on. This is, again, inherently in there. And at the youth levels and the college levels, there are no rules that would prohibit this from football. But NFL, maybe. We found it's useful actually in COVID because nobody was playing football when we were developing this. It's great for package delivery workers, people in warehouses, anytime you got to carry something, even healthcare workers doing physical therapy. If you've got to move a heavy patient, it helps you grab them. And
right. So then you don't have to squeeze as hard to boost the friction because you're getting the friction for free from the material.
Correct. It's got the tackiness built in.
And that's all in the weave.
It's in the weave. Exactly right.
Yeah.
So, okay, so far this show, we've learned that cooking for materials is good, and now it's knitting.
Yep.
Okay.
I mean, you've gone back to the future. There's some simple things that we do that achieve amazing things now.
So there's only so many ways you can fabricate things, and it's adding a new, recipe from our spice rack. The periodic table is my spice rack, so I can pick and choose things from there to yield the ultimate performance.
Here's what I want to do. I want to have another show on the other side of the house, StarTalk flagship, where we just talk about the geeky things you can do with the periodic table of elements and what goes through your head when you walk up to that spice rack.
Sign me
say,
up.
Today I want to make this. And I just want to have a conversation with you. When you make 2 parts silicon, 1 part oxygen, 3 parts carbon, I want to have that conversation. Will you come back for us to do that?
I will. I've got my periodic table right here.
Never leave home without it.
Right there.
Excellent. We got to call it quits there. Jud, it's been great having you on this. We love geeking out with you here. And there's no end of sports. Maybe we'll get you back during the Olympics and we'll be right in the middle of what's going on.
And figure out all the ways that the things you've come up with will not be in the Olympics.
Well, the blades on the skates. Everybody thinks those are flat. They're not flat. They're concave. So you actually got two little blades on the edge.
We did a whole show on that.
We're there.
So cool.
We've done that. Yep.
Good.
We did a whole show on that one. So, all right, dudes, we're calling it quits there. Chuck, Gary.
Always a pleasure.
Pleasure, my friend.
All right, this has been StarTalk Sports Edition. Neil deGrasse Tyson, your personal astrophysicist, bidding you to keep looking up.